All right, Honors Chem, today we are going to talk about reaction kinetics. In other words, it's called rate law. So basically, today we are learning about why reactions happen and how fast they happen. And we're also learning about how we control how fast or slow something happens. Okay, so let's get in with collision theory really quickly. So collision theory is basically the idea that in order to react, molecules actually have to collide with each other, okay? So to react, molecules, and they really could be molecules or atoms or ions as well, must collide with each other. Okay, so here's an illustration here. If I have molecule AB and molecule B, or molecule A2 and molecule B2, they collide and I will get two AB molecules. They're not going to react to make AB molecules unless A and B actually come together and collide. Okay, so that figure is an illustration of collision theory, which states that atoms, ions, molecules must collide in order to react. However, think about this. Most collisions fail to produce products. So if I have A and B and they collide with each other, most of those collisions actually don't make ABs. So why? Think about that for a second. Is every collision going to be with the right molecule at the right place? No. So we have to have the molecules actually hit each other at the right spot. Think of this as a demolition derby, if you've ever been to a demolition derby. If you've ever been to a demolition derby, the idea is to have your car functioning and still drivable while making everyone else's car undrivable. So if I smash my car into the trunk of another car, is that going to make the other car undrivable? No. I need to hit the engine, but I need to hit the engine with something that doesn't make my car undrivable. So we need to hit the right spot, okay? So we must have the proper orientation. So it means that the molecules must be oriented so that they hit on the right spot of each other to actually react. And what happens if I try and hit in a demolition derby and I'm only going like 5 miles an hour? Is that going to damage any other car? No, I need to hit with enough force to do damage. So the collisions have to have enough energy to actually create a reaction. So collisions have to have enough energy. They must have enough energy to create what we call the activated complex. Okay, so that activated complex right here is this kind of halfway molecule where bonds are being broken on the old molecule, and that takes energy to break bonds, and bonds are being made on that new molecule. So we've got to have enough energy to start breaking old bonds and making new bonds, and that is the activated complex, that kind of in-between molecule. Okay, so let's look at some more illustrations. These illustrations down here indicate that in order for a collision to lead to reaction, the carbon atom in the carbon monoxide molecule must actually contact an oxygen molecule in the NO2 molecule to make carbon dioxide. That's the only way in which a temporary bond can form between the carbon atom and the oxygen atom. So if I have a carbon monoxide molecule reacting with a nitrogen dioxide molecule, if I have it hit where it hits another oxygen molecule, those oxygens, I don't need a bond with an oxygen to an oxygen, I need to create a bond with an oxygen to a carbon. So this is going to rebound here because it's not hitting on the right spot. If I have the oxygen hitting the nitrogen on the nitrogen dioxide, once again, I don't need the oxygen side of the carbon monoxide hitting nitrogen. I need the carbon side hitting an oxygen. So if I have the oxygen side also hitting the nitrogen, that's going to rebound. But if I have the carbon side hitting an oxygen, I can create that activated complex if I hit hard enough to form the products of carbon dioxide and nitrogen monoxide. Okay, so I have to have the correct orientation. I also, even if I have the correct orientation, if that energy, if that collision is not full of enough energy, it's just going to bounce off. Think about this. How many of you guys, when you were little kids, played with Hot Wheels cars? Did you play with those? How many of you guys created that track where you had to go and do that loop-de-loop? Like it came down and you loop-de-looped it. If you didn't have enough energy from the height that you had that car going down before it hit the loop-de-loop, that car would just go up and then come back down. It wouldn't have enough energy to go around that loop-de-loop. So we have to have enough energy for that reaction to actually take place, to create those new bonds and start destroying those old bonds. Okay? So the minimum amount of energy to actually have that old bonds being destroyed and new bonds created, that minimum amount of energy right here that reacting particles must have to form that activated complex and lead to a reaction is called the activation energy. Oh, and I can't spell. Okay, and we abbreviate that as E sub A. Sometimes I will actually write it E sub capital A like that as well. Okay, so summary of collision theory. Reacting substances, the atoms, the ions, the molecules, they have to collide, okay, in order to react. In order to get that reaction to be successful, they have to collide with the proper orientation or the correct orientation. The right part of each molecule has to hit the right part of the other molecule, okay? And reacting substances must collide with enough energy to form that activated complex. You've got to have enough energy to break old bonds and start making new bonds, okay? So we're going to start looking at these potential energy diagrams. So notice that on the y-axis, we have energy, and this is called potential energy. And I really can't spell today. Potential energy. Okay, and then along the x-axis, this is really time. Okay, this is how the molecules react through time. Okay, so I want to just go along and talk about what we're seeing in this, in these diagrams really quick. So let's look at the first one on the left. The figure on the left is an energy diagram for carbon monoxide making a connection with nitrogen dioxide. We make that activated complex, and then we get carbon dioxide and nitrogen monoxide. So here is where our reactants are. This is the energy of our activated complex. So right here, this is the top. To the top is the potential energy of our activated complex, actually. Let's actually draw that better. So this to here would be the potential energy of our activated complex. This is our potential energy of our reactants. So this is the energy that our reactants start at, the potential energy. Okay, this right here is the potential energy of our products. Okay, so we've got potential energies. Notice that our potential energy of our reactants is much bigger than our potential energy of our products. That means we've actually put energy to the outside of this system. So this is what we would call an exothermic reaction. Okay, we are releasing energy when this reaction happens. Okay, so this is an exothermic reaction. Okay, is it going to let me write? So this we would call exothermic. So if the potential energy of our reactants is greater than our potential energy of our products, that is exothermic. Okay, also here, look at the energy that it takes to get from where our reactants are to that activated complex. Right there, that green line, this is our activation energy. Okay, so that green line is our EA. That's how much energy I've got to put into that system to even get that reaction to go, to even start. Okay, and then let's look at this. The difference between our reactants and our products. So the potential energy of our reactants minus, or let's actually do it different. Let's do it backwards. The potential energy of our products, so that's our products minus the potential energy of our reactants. This is the enthalpy of the reaction. Sometimes this is called delta H. So if the delta H is negative or less than 0, we have an exothermic reaction. If that delta H, on the other hand, though, is greater than 0, we have an endothermic reaction. Okay, so let's look at this graph over here. Our reactants have much lower energy than our products, right? The potential energy here. So that means that our delta H is actually positive. We had to put energy in here. So if our delta H is positive, it's an endothermic reaction. Okay? The other thing, look at how much bigger our activation energy is on that. We had to put in a lot of energy even to get that reaction to go forward. Okay? Our activated complex, though, is still at the same level. Our products, let's see, what else do I need to show you guys? Now, if you look at these two graphs, they're basically reverses of each other. So I could actually just look at this first graph and say, I want you to read it as a forward reaction, and this one's an endothermic. And I want you to, then I could say, I want you to read it as a backward or a reverse reaction. So notice that when we do forward and backwards, it's really the same. Most of these reactions are reversible, so we can read these graphs forwards or backwards. Okay? So below the figure is an energy diagram. Match the appropriate number with the quantity that it represents. Okay? So our reactants, this would be A, that would be our potential energy here. Our activated complex, this would be B up here. my gosh, it's not letting me write. And our products, this would be C right here. And our activation energy would be that green line right here. Okay, so we talked a little bit about that. Okay, let's look at this next graph. Okay, let's look at number 2. Let's label all of these things. So number 2, that's our potential energy of our reactants. So that's our potential energy of our reactants. Number 3, if I do this whole line all the way to the bottom, if it's going to let me do that, this is our potential energy of our activated complex. Okay, looks like it erased what I had here. So number 2, this is my potential energy of my reactants. Okay, this number 4 is my potential energy of my products. And line number 1, this is my activation energy. So that's my activation energy with the forward reaction. If I wanted to do my activation energy of my reverse reaction, I'm going to see if I can make this bigger. I would have to kind of eyeball this. That would be this line. So this would be my activation energy of my reverse reaction. Okay. And then let's see, what else could we do? We could also do our enthalpy of this reaction. The enthalpy is the difference between the products and the reactants. So this is my enthalpy, or my delta H, the energy in here. So forward, if I looked at my forward reaction, is this endo or exothermic? Am I putting energy in or am I taking energy out? I have to put energy in, right? So my delta H is positive. My delta H is positive. So that means I have an endothermic reaction. If I look at my reverse reaction going this way, my delta H is negative because I have less energy at the end. So that is exo. That's an exothermic reaction. Okay? So that is how you read these graphs really quick. So we have delta H that we can read. We can have products. We can have activation energy of forward, activation energy of the reverse, potential energy of the reactants, where the products, where the activated complex is. This is the activated complex. Always at the top of the energy graph is where that activated complex is going to be. This is reactants and products. Okay, so lots of little things that we can get off of these graphs. Okay, so let's talk about some factors that affect the reaction rate. Like I can change how fast a reaction goes. I can slow it down, I can speed it up. Okay, so let's look at some factors that affect the reaction rates. Nature of the reactants. Some substances react more readily than others. For example, copper and zinc are both metals, and they have similar physical properties because of their relative positions on the periodic table. They're right next to each other. But they react at different rates when placed with aqueous silver nitrate in solutions of equal concentration. Okay? Ions in solution react almost instantaneously to form precipitates, while molecular compounds tend to react more slowly. So the reason that ions react almost instantaneously, think about how small a little ion is. There's only like how many places to hit an ion? Not very many, small. But if I have a whole big molecule, let's talk about like a sugar molecule. If I have a sugar molecule, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons. I'm going to have all these oxygens off of it as well. And if this right here is where it needs to be reacted and hit, think of all these other places, and I'm going to change my color. Think of all these other places that I could hit that molecule. So it takes a lot, the probability of hitting the right spot becomes a lot less on a big molecule than it is a little tiny ion. And because of that, the smaller the molecule, usually the faster it can react, just because the probability of hitting that reaction site is so much better. Okay? Concentration. One way chemists can change the rate of a reaction is by changing the concentration. Okay? Remember, the collision theory states that particles have to collide in order to react. So, the more particles that are present, the more probability I have of collisions, right? If I have a molecule concentration that's really, really low, the chance of other molecules actually finding a molecule and hitting it and colliding are low. So the more concentration I have, the more chances I have for collisions because I have more molecules in there. Okay? So the more particles that are present, the more often those collisions can happen, and the more chance I have of actually having a successful collision. Okay, and this is still frozen. Okay, sorry. Give it a minute, hopefully. Okay, so think about it this way. Think about a burning candle in a room of 21% oxygen, okay, as opposed to burning a candle in a room of pure oxygen. So I upped the probability 5 times, making it pure oxygen instead of just 21%. 100% versus 21%, it's like a 5-time increase, okay? So we will spend a considerable amount of time with concentration and reaction rates and how that affects in the next couple days in our notes. Okay, surface area. You've all probably seen that things that are crushed up with small little surface area makes it a lot easier to react because the reaction can hit all over unless it's all bundled together in one big clump. Think about a wooden fire, okay? If I have a log on a wooden fire, where can that fire actually burn the log? The oxygen from the air can only burn the log on the surface, right? That's why when we do a fire, the logs burn from the outside in, right? Only the surface can burn. Now suppose I took up a log and I ground it up. I put it through a mulcher machine and I had a whole bunch of sawdust. What would happen to the rate of that fire? Now the oxygen can actually hit every little surface of all that wood all at the same time, right? Because it's sawdust. Which would burn faster? Sawdust would actually create a fireball, okay? Because of the increased surface area. That allows it to react a lot faster. The greater the surface area of the sawdust allows the oxygen molecules to collide with the wood molecules everywhere along that whole entire surface. So it makes it very, very combustible. All right, next thing, temperature. Increasing the temperature of the reaction generally increases the rate of the reaction. For example, you know that reactions cause food to spoil faster at room temperature than if we put them in the refrigerator. That's why we put the food in the fridge, to slow down that spoiling process, right? So let's look at the reaction rate and temperature. So if I have the temperature go up, notice what happens with the reaction rate. Okay, it goes up. Okay, think about it this way. When temperature goes up, right, on T2, look at how many more molecules I have that actually have the kinetic energy to make that reaction happen. I get a lot more molecules. And because I have more molecules that actually have enough kinetic energy to make that reaction happen, I have more successful collisions. It's once again a game of probability. Okay? More are able to do it, so the probability of a successful reaction goes up. Okay. Next, catalysts. Many chemical reactions in living organisms would actually occur so slowly that we wouldn't be able to sustain life at normal living temperatures. So our enzymes are living catalysts. They make the reactions that we need to live go about 20,000 to 100,000 times faster than they normally would. Life would not happen without enzymes, okay? Enzymes are a type of catalyst. You've probably heard of catalysts before. Like we have catalytic converters on our cars that catalyze some of the waste products and make them a little less harmful once they come out of the tailpipe of our car. Okay? A catalyst is just a substance that does not get used up in a reaction, but it helps that intermediary step, that activated complex, happen at a lower energy. Okay? It increases the rate of chemical reaction without being consumed. So for example, if I put a catalyst in a reaction, notice that the activation energy with a catalyst is way lower than the activation energy without the catalyst. And because I make that activation energy lower, that means more molecules are actually going to have the kinetic energy to overcome that energy barrier and have successful collisions. I'm going to put some videos with demos of catalysts, surface area, and I'm going to try and find a concentration video just so that you can see how much concentration, surface area, and catalysts actually affect the reaction. Okay, so those are all the things that we can play with to get the reaction rate to either speed up or slow down. We can put in a catalyst, we can play with the temperature, we can play with the concentration, okay, we can play with the surface area, all of those kind of things. Pressure, this only happens for gases, okay? It's the same as concentration. Think about gases. If I put a lot of pressure, don't I push those gas molecules together? I increase the concentration. So if I increase the pressure for a gas, I also increase the concentration. If I decrease the pressure for gases, it's the same as letting those gases expand. And if I let those gases expand, I decrease that concentration. And if I decrease that concentration, the probability of having even a collision, because the molecules are so far apart, becomes much lower. Okay? All right, so next time we are going to start talking about concentration and how it affects rate law. So get ready to do some rate law and some more math. We'll see you later. Have a great day. Bye.